Hello and welcome to the MOOC module on optical communications. In this module we will complete the discussion of noise in photodiodes and then discuss the signal to noise ratio aspects of a photodetector circuit. Okay. We will not look at the actual circuit, that is reserved for some time later. What we will do instead is to assume that there is just a load resistor of some value RL and the current that is generated by the photodiode actually flows through this RL and then generates a voltage or a current depending on whatever you are looking at, and that is what we are going to use as the benchmark. Okay. So, we will see what happens when this large when the load resistor is large and when the load resistor is small, what kind of noise limits our signal to noise ratio. Okay. We have discussed several intrinsic noise processes in a photodiode, right, but when you include a load resistor RL, so this is the load resistor RL, there is actually a noise associated with a resistor which is kept at room temperature. Okay. This noise is called as thermal noise, and this is purely because of the motion of electrons inside this resistive material as a result of thermally generated energy. So, any matter kept at the energy or temperature T greater than 0 will experience a certain amount of energy, and as a result of which there will be a vibration or there would be some jiggling of the electron hole pairs constituting current or equivalently a voltage, resulting in in addition to the actual voltage or the current that is in the resistor, there is also a noise because of this irregular motion of the electrons. So, the current is not exactly a deterministic process, but it becomes stochastic or statistical because of this thermal noise. If you look at thermal noise, you are mostly interested in knowing what is the variance of the thermal noise, right. So, what would be the range over which I can expect the current to be in, right, and this thermal noise variance surprisingly is independent of how much current you give to the load resistor RL, okay, or to any resistor R. It is in fact simply proportional to the thermal energy that it receives, which is kT, right, which is proportional to kT, and then divided by RL. This is divided by RL because you are looking at noise in currents, okay, you are looking at current noise variance, but if you are someone who is looking or you are comfortable with looking at the voltage noise variance, it would be 4 kT into RL, because current square into RL is voltage. So, that can be related to the power V square by RL, and therefore, you get voltage noise variance as 4 kT into RL. But because photodetectors mainly generate current, we will look at the current noise variance. Okay. The expressions will involve divided by RL quantity. Okay. And you can see that it does not depend on how much current you are actually providing through the load resistor, it does not depend on any of that parameter, it in fact does not even depend on the precise shape of the resistor. Okay. All that shape and everything is captured in this RL, and it simply depends on what is the value of the resistor and what temperature this is working in. Okay. In addition to this thermal noise, we have seen short noise in both PIN as well as APDs, although with APDs you also get a multiplication noise or a multiplicative noise, mainly because of this multiplication factor M. Okay. Now, we define signal to noise ratio, which is a very important term in all communication systems, because you want communication systems to have a very high signal to noise ratio. You want much of the signals that you have received to actually be the signals that you are looking at, and not this fluctuations which you do not have any control or you do not have any use in obtaining the information, right. So, you want the signal to be as large as possible, noise to be as small as possible. The way we define signal to noise ratio is that we define this as the average signal power, okay, to the noise variance, which can be thought of as the average power that is dissipated in a 1 ohm resistor. Okay. If I have a photocurrent IPH, okay, what would be the power that is noise power that is generated, average noise power that is generated in a load resistor RL? Well, IPH square into RL would be my average power that is generated, right, assuming that this IPH is in the RMS value or something. So, you get RMS IPH square times RL will give you the average signal power, right. This would be the signal power. What would be the noise variance? Well, you have short noise and you have thermal noise, right. So, you add up the variances there, but what should I add there? Should I add it over an infinite bandwidth? No, I am going to add it over the bandwidth of the detector itself, right. So, we have assumed that the detectors have a bandwidth of BE, the low pass bandwidth of BE, and therefore, the two sided bandwidth is about 2 times BE, right. So, for that the amount of noise power that is added will be multiplied by the sparse spectral density. Here in the thermal noise you multiply this one by BE. This is simply because you are looking at a bandwidth of 2 BE in fact, and I had written down the variance. This 4 kT by RL is actually the power spectral density. So, this is power spectral density. Okay, the power spectral density is constant and wide and it is independent of current 4 kT by RL, but if you consider a two sided bandwidth of 2 BE, then this would be the thermal noise variance. Okay. And because this noise process is actually nothing to do with the current, the variance is actually not 2 times BE, but rather only BE. So, this is actually the noise, thermal noise variance that you are looking for. Okay. So, you can now write down what is the noise variance, which is the sum of short noise as well as the thermal noise. So, let me write down those terms. So, you have 2Q IPH plus ID, assuming that dark current is there. If you do not have dark current or you can neglect dark current, you remove ID from the equations, right. So, you have IPH plus ID, this is for the short noise times the bandwidth BE that you have, and all this noise is in the load resistor RL, plus you have the thermal noise variance, which is 4 kT by RL into Fn BE, where Fn is called as the noise figure of the resistor. It is the degradation in the signal to noise ratio that would be experienced. So, it is not just 4 kT by RL, but there is a multiplication of this quantity by an additional noise factor called Fn. Okay. In fact, Fn is what is called as the excess noise figure, and that is something that represents the degradation of the signal to noise ratio at the input and the output. Remember, output signal to noise ratio is always lesser than the input signal to noise ratio, and the amount by which this is lesser is proportional to this noise figure or noise factor, depending on how you actually call the ratios up there. Okay. So, this is what you have, 4 kT by RL into Fn. This would be your noise variance, and this is your signal to noise ratio. Now, signal to noise ratio is given by this expression, but you might be tempted to see if there is any range over which one variance dominates over the other variance, right. So, if I try and make RL to be very large, then the second term kind of starts to go down because it is inversely proportional to RL, while the first term kind of goes to go up, right. In that region you are in what is called as the short noise limit. The opposite is true. If your photocurrent is small, right, and your RL is moderate to small, then the thermal noise component will dominate over the short noise. So, you get two limits in practice, you get a thermal noise limit and you get a short noise limit. Okay. Most pin photodiodes are operated in the short noise limit. However, APDs actually have a very high internal short noise, because remember, whatever the current electron hole pairs are generated, because of the impact ionization and the avalanche process, multiple photocarriers are generated. So, the mean photocurrent increases and the internal short noise variance of an APD increases. Okay. So, your APD circuits are mostly operated in the thermal noise limit. So, we will see both noise limits and see what is the expression for the signal to noise ratio. So, first consider the thermal noise limit, okay, which happens when your RL is quite small. So, the first term, the short noise term, can be neglected with respect to the second term, right. So, this can happen when the photocurrent IPH is quite small. Okay. So, in the thermal noise limit, we assume that the short noise variance is small compared to the thermal noise, and the SNR becomes IPH square RL divided by 4 kT by RL Fn into BE, and you can see here that the thermal noise limit, I multiplied by RL in the denominator and the numerator, but I forgot to remove this RL from this expression. Okay. So, it is 4 kT by RL Fn Be, but there is no RL originally in the short noise variance, correct. Short noise variance is 2q IPH plus ID into Be. So, when I multiply RL by numerator and denominator, I should have removed this, I did not remove it. So, now I am going to remove it and then go back to the expression for thermal noise limit. There is, so this RL is not here. So, let me remove this one from the consideration. Okay. So, this is your thermal noise limit, the signal to noise ratio. How is the photocurrent generated? Photocurrent is generated because of the responsivity of the photodiode times the optical power that is incident. So, IPH square is basically R into incident optical power square, and what you observe here is that the signal to noise ratio when you are looking at the thermal noise limit, okay, is directly proportional to RL. In fact, you can increase the signal to noise ratio by increasing the value of RL. Do not be so surprised because increasing RL only reduces the thermal noise variance, right, because it is inversely proportional to RL. Therefore, thermal noise variance reduces. However, as long as even this reduced thermal noise variance is larger than the short noise variance, you are still in the thermal noise limit. Do not increase RL too much, otherwise you will go to the short noise limit, right, because RL increases and the short current noise actually decreases completely. So, this thermal noise, in the thermal noise limit you can actually use a larger resistor RL and increase the signal to noise ratio only up to a certain limit, of course. Okay. Let us go to the short noise limit, and in the short noise limit what happens is that the thermal noise can be almost neglected, the load resistor RL is quite high. Okay. How do you obtain a large RL? Physically you can take a big resistor and put it there, okay, but in practice you implement what is called as a trans impedance amplifier using an op amp, and op amps have a very high input impedance. Okay. So, because of that reason your PIN photodetector circuits are normally short noise limited, they are not usually thermal noise limited. Okay. So, in the short noise limit what happens is that the signal to noise ratio in the short noise limit is given by the photocurrent, which is R into P incident, which is the optical power incident, times RL divided by 2q IPH RL into BE, right. So, here you can see that RL in the numerator cancels with RL in the denominator, so that is gone, right, and IPH in the denominator cancels with one of the IPH in the numerator, because IPH is R into Pn, right. So, this also cancels out here and the square term goes away, and then what you get is a nice short expression in which you can see that the signal to noise ratio is actually proportional to responsivity. But if you remember, responsivity itself was proportional to quantum efficiency, right. So, it is eta q by hc something. So, it is directly proportional to quantum efficiency eta. So, the short noise signal to noise ratio can be increased by increasing the responsivity R or equivalently increasing eta, and it does not really care what is the load resistor that you have kept, as long as that load resistor is quite large. Okay. So, that thermal noise limit is all gone. So, this is the short noise limit for a PIN structure. However, for APDs the situation is slightly more complicated, because for APDs the signal to noise ratio in the short noise limit is actually dependent on RL. It is given by RL. As I said, APDs actually operate in the thermal noise limit. So, it is proportional to RL, but you actually, if you put in the multiplicative terms and write down the short noise variance terms there, you will see that this is given by RL R square 4 kT the excess noise factor Fn times Be. This entire thing gets multiplied by m square. So, this R into P incident is nothing but the photocurrent IPH. So, this is IPH square, but what you see here is that there is a multiplication factor m square which is impacting over here. So, if you want to increase SNR, you can increase SNR by operating the APD with a larger multiplicative gain. However, larger multiplicative gain also has some effect on the excess noise factor F, right, because we have seen that F versus M curves for a APD, depend also of course on the additional factor k, but in case you look at it, they are actually linearly increasing. So, for larger value of k. So, there is actually a optimum value of the multiplication factor m, which makes the SNR highest. For a given optical input power, you can maximize this multiplicative gain, okay, which you can obtain by going back to the short noise variance and then differentiating that with respect to m and setting the resultant expression to 0. You will end up with a cubic polynomial equation, okay, which gives you the value of optimum value of the multiplicative term m. So, you get this term by going to the equation for the APD noise variance and then differentiating that with respect to m and setting it to 0. I will just leave it as an exercise for you to do that. It is a straightforward exercise. The resulting expression is a little bit tedious, but you get here, this is the thermal noise variance, correct. 4 kT Fn by R is the thermal noise variance divided by Q R P in, right. I am of course neglecting the dark current in all these expressions, and you can actually see that if you plot the incident optical power, okay, and m in terms of the optimum value of m for different optical powers which are measured in dBm, you will actually see that the optimum value of m decreases as incident optical power increases, okay. So, this happens for k equal to 0, and these are the values for increasing value of k. Remember that k is the ionization parameter dependent constant k, okay. So, this is for the APD. There is one additional factor by which we, or additional term by which we quantify the photodiodes, and this additional quantity is called as the noise equivalent power. Noise equivalent power is a situation where the noise variance actually is equal to the optical input power, or you can, as you start reducing the optical input power, you will come to a situation where the signal to noise ratio becomes exactly equal to 1, at which point signal power is equal to noise power. So, there is actually no improvement in the, or there is no way in which you can distinguish signal and noise out there, because they both are equal to each other, and the minimum optical power at which the SNR goes to 1 is called as the noise equivalent power, okay. So, this noise equivalent power can be obtained by setting the SNR in the thermal noise limit to equal to 1, right. So, if you do that, what do you get? You have the incident optical power divided by the bandwidth is equal to 4 kT Fn by RL, which is the noise variance, divided by R square, R being the responsivity, right. So, you can take this R to the numerator onto the left hand side and you get IPH square, right, and that is what I have just rewritten the equation. Then what we do is we take the square root on both sides. So, if I take the square root, I get the minimum optical power, okay, per square root of bandwidth, okay. This should be equal to 4 kT Fn by RL divided by responsivity R. So, this is to the power half, okay. This fellow which is on the left hand side, which represents the minimum optical power per square root bandwidth, is measured in terms of, typically in terms of pico watt per square root hertz. The typical values are anywhere between 1 to 10, although some very good photodiodes have reached the range of femtowatt per square root hertz, okay. If you know what is the total bandwidth of your circuit, then take the square root of the bandwidth of the circuit, multiply it by the NEP, that tells you what is the minimum optical power that is necessary in order to make the signal to noise ratio equal to 1, and then you can choose the optical power that you are going to input to the detector to be, let us say, 10 times NEP, 20 times NEP, and so on, okay. So, if I have a bandwidth of 1 gigahertz, then I take the square root of that 1 gigahertz bandwidth, multiply it by this 1 picowatt per square root hertz term. So, I get the minimum optical power that is required to make SNR equal to 1, but of course, you never operate your circuits with SNR equal to 1, you operate circuit with an SNR of say 10, 100, and then you can scale up the required optical power. So, that is the essential use of NEP. Associated with NEP is one more factor called detectivity. So, if detectivity is simply 1 over NEP, and it simply tells you that if this is the optical power, whether this optical power will be detected or not, okay. So, it tells you how the noise is greater than signal. So, if you get a very small NEP, then the detectivity will actually be very high. Okay. So, this completes our discussion on noise in photodiodes, and in the next module we are going to discuss the optical sources, and then we will come back to combine optical sources, modulators and the WDM components that we have discussed, and then put in the receiver at the end and then analyze what will happen to the systems. Okay. Thank you very much.